Hello, everybody, and John. This gave me a chance to think back on the early years about what we were doing and what we were up to back then. So this has been a joy and fun to put these view graphs together. So I think I'm calling this the John Castor in the early years of high energy density, and I'll end up calling that HED, laboratory astrophysics, and how you see it has evolved into what's going on today. And I'll try and get to some of the new things we're doing on NIF to show you that. Let's see, so in the early years, I was working in the ICF program, Laser Inertial Confinement Fusion, or Laser Fusion, on the NOVA laser back then. And the NOVA laser in those days was the world's largest laser. And of course, we were very happy to work on it as experimentalists and very proud of the fact that it was the biggest laser around. In 1993, what happened is that almost all or most of the experiments for ICF, which had been classified, at least indirect drive, whole room driven, X-ray driven ICF had been classified, that all became unclassified. So suddenly we could talk to the outside world about our work. And also there was some desire to get some university collaborations going and bring in some outside people to lead projects. And so they created the Science Use of NOVA program, which allocated about 10% of the laser time to a proposal process, and it allowed outside people to propose, preferably from universities. And so we started working with that. And that's when I formed a team to start studying some supernova dynamics. I quickly made friends with John Castor, who I learned about from Dave Dearborn, and he said, you should be talking to Castor because I wanted to do laboratory astrophysics. So I talked with John Castor. I met up and teamed up with Dave Arnett and his grad student at that time, Jave Kane, and Dick McRae, actually. And so I met Dick McRae, I believe it was, at the La Serena conference, which was the 10-year anniversary of supernova 1987A. And Dick was interested in supernova remnant evolution, as you just saw. And we were interested to start dynamics experiments related to the actual explosion evolving into the remnant, so all of the above. And we met at the La Serena conference in Chile, which was a lot of fun. And that's where I presented some of the early results and some of the ideas I thought would be fun to develop. And you can see a couple of papers there with John Castor, Jave Kane, Dave Arnett, Gail Glendenning, I can see is sitting. I just saw her back there, so I needed a very skilled experimentalist, so we didn't make a mistake on this outside experiment with the astro community. So I put our top experimentalist on it to make sure the experiment worked. That was Gail. Dick McRae's on one of those papers, I believe, where we were looking at the evolution all the way into the remnant regime. And so the experiment worked very well. I'll show you some results from that, and then I'll switch to, we shut NOVA down, we built NIF. It took a few years to get NIF built and up and running, and then I'll show you some results, or at least some of the projects that we're doing on NIF. So the very simple idea, and at the time I picked this plot for two reasons. The plot on the right is a single mode Rayleigh-Taylor evolution of the Rayleigh-Taylor instabilities evolving from the helium-hydrogen interface, I believe, or it might have been the carbon-oxygen interface with helium, of a core collapse supernova. I think it was a type 1b, 1c, so I guess no hydrogen envelope. So it was the carbon-oxygen pushing up against the helium, that interface. As it gets decelerated, it's Rayleigh-Taylor unstable. They put a single mode perturbation on, and you can see the evolution into the deep nonlinear regime. So I took that, and then I found this is right around the time when ICF was just being declassified. So I was looking for a direct drive experiment to show in a view graph. So the left-hand side is a direct drive ICF capsule implosion done by Sakagami and Nishihara at the Osaka University. But what struck me is that just the instability evolution to me, the Rayleigh-Taylor instability evolution to me looked very similar. It's simply one was going outwards, explosion, and one was going inwards, implosion. But my reasoning was the hydrodynamic instability part, which is what I was measuring and interested in, it seemed to me, had to be similar. So we struck up this collaboration. We brought in people who could help us design the laser experiments and people from astrophysics who might be interested. So by that time, I had started talking to John Castor, and I started to learn who the people were I should be looking at and reading. So there's this very nice paper by Ewald Mueller, Bruce Frixell, and Dave Arnett that produced the multi-mode nonlinear Rayleigh-Taylor instability evolution in a simulation of 1987A. And you can see it's a multi-mode evolution. Since I'm still involved with hydrodynamic instabilities, you can see the evolution of a multi-mode pattern getting more and more nonlinear, and as the nonlinearity grows, the larger Rayleigh-Taylor bubbles consume the smaller ones, so you get bubble merger, which means the bubble patterns are getting broader, and that happens, and you get this dominance of the larger modes. And so that whole nonlinear hydrodynamic evolution with bubble merger, making the scales get larger, is of interest to us at DOE as well. So it's a perfect match with a connection to the outside world and a connection to the inside world, something we're interested in doing. So this idea, once we got going, seemed like it was going to take off and go. And as I said, Gail Glendenning helped with the first experiments, maybe all the way up until when NOVA was shut down, I think. Gail, you're welcome back, by the way, because the experiments are continuing, and we'd love to have you out there. A few more simulations. This shows what I would call the interfaces in a target physics point of view. Here's the core, there's the carbon-oxygen layer pushing up against the helium layer. So in what I just showed, it's this interface, what I call interface, between the core and the helium that was unstable. In a normal type 2 supernova that has a hydrogen layer, the helium-hydrogen interface is also unstable. So you have two unstable interfaces that are evolving and mixing, and you get these nice Rayleigh-Taylor spikes jetting out. And you also get the effects of decompression as the star is expanding. So even in a 1D sense, the envelopes would be expanding because of the decompression effect. And when you make measurements, you have to take into account both. So the same two papers are cited here. So we wanted to do an experiment, and I needed help, both from the astrophysics community, so I knew what I was doing. And you can see Dave Arnett, Edison Liang, Dick McRae, John Castor, since he was on both sides of the camp, and I needed what we call a designer, someone to do simulations of the actual experiment on the NOVA laser, and so John Castor could do that, and so I needed someone to run a rad hydro code to calculate what we call the drive, which is the initial shock, and then the interface versus time, the interface position versus time, the unstable interface position versus time, so you can measure the velocity versus time, and the deceleration, so you can calculate the Rayleigh-Taylor instability. And you can see the interface. This is from a simulation from John. And so you can see the interface and the evolution. Here's velocity versus time. In this case, I had a copper plastic. I had to get a target made. It couldn't be expensive, at least for a first try. So I said, we'll make the target out of copper and plastic. There will be a density mismatch. We'll blow it up like the supernova does, but we'll do it in planar geometry. We'll measure the velocity versus time of the interface. It'll be decelerating, so it's Rayleigh-Taylor unstable. As you see here, that's velocity versus time. And then we'll put a ripple at the interface between the copper and the plastic. And just like in the star that's exploding, the ripple will grow by the Rayleigh-Taylor instability, and we'll measure it with side-on radiography, just like you're looking here. So Gail's job was to go out and do all the alignments so we could take a nice image. And the actual experiment is shown here. The image was taken somewhere. I wrote the time. I don't see it here. It was taken at sort of 20, 30 nanoseconds later. Oh, there it is, 30 nanoseconds. So we took the image at 30 nanoseconds. You can see the Rayleigh-Taylor there. And the two things that are happening, the Rayleigh-Taylor instability caused the perturbation to grow. Plus, as it expands, it's decompressing, and that's also causing it to grow. And then we calculated that. The data points, the experimental data points are showing the bubble and spike fronts, and then the calculations of the interface position and the bubble and spike fronts. So that was our first experiment. And John helped us with the simulations. Gail did the experiments. It worked really very well. We got lots of nice papers written out of this and talks that evolved out of it. So it was fun. And then with both John and then later with Dmitry Ryatov, we worked out the scale transformation mathematically from the Euler equations to show how to relate the laboratory scale, 100 microns, to the star scale of light years and hours of evolution as compared to nanoseconds. And that all worked out very nicely, and you can work through that scale transformation. And as long as radiation was not a dominant effect, it scaled very nicely. This was the ICF, the inertial confinement fusion I was working on that led into that supernova experiment. And the one thing to note here was kind of a, it didn't dawn on me the meaning of this particularly, but if you look back at what I'd call the classical instability evolution, this is a simulation and the experiment actually shows it. You get this bubble spike shape and the Rayleigh-Taylor spike tip evolves into this vortex structure that's classic hydrodynamic instabilities. When you do the same experiment in ICF where you have an X-ray drive and the interface is the ablation front now, you get the Rayleigh-Taylor instability, but you don't have that tip broadening into that vortex structure that's classic for Rayleigh-Taylor. And I never thought a lot about that. But I'm going to show one new result. I'm going to have to go forward and then come back. I'm going to show one new result from NIF. So let me do that so I don't get cut short, and then I'll come back. It's here. So we got to NIF, and a team led by the University of Michigan and led by the University of Michigan and paired up with Israel, an Israeli national lab, Dov Schwartz in Israel, Carolyn Karantz at Michigan, teamed up and said, let's do a similar experiment that we did on the supernova Rayleigh-Taylor on NOVA. Let's redo it on NIF, but let's make the strength of the shock strong enough. After all, when the star blows up, it's a very, very strong shock. Let's make the strength of the shock that blows up that interface and causes the whole dynamics to start strong enough such that the shock moving forward into the low density medium, so the shock is going through plastic into foam here. So that'd be like the strong shock from the core collapse going through helium into hydrogen, or from carbon into helium. Let's make the shock strong enough that the shock is a radiative shock. So at the shock front, it's hot enough and it's still dense enough that it's a copious source of soft X-ray or UV radiation because it's a radiative shock. It's a very strong shock, and it's radiating. So if the shock is strong, by the radiation behind the shock, it ablates the spike tips, and it becomes this stubby thing. So the peak to valley of the perturbation is smaller, plus that classic rolling up vortex, which in Fourier space would be a lot of higher modes, all gets ablated to stabilize, and it doesn't happen. So just by the strength of the leading shock, whether it's radiative or not, you can change the amplitude of the perturbation and also its actual shape, which I thought was quite cute. And then the question immediately emerges, well, in astrophysics, typically they would not be doing the radiative transport behind the shock front. So, does this effect of the radiative shock modifying the perturbation growth affect anything in astrophysics? I don't think we know. This is a new result. It was just submitted to Nature Communications, I think. I think they just responded to referee comments, so I think it's going to be accepted. So it's new. The experiment was cute in the sense that it worked quantitatively, and qualitatively it showed you this interesting result. And now we'll have a chance to play around to say, does that have any impact on astrophysical settings? We haven't gotten that far yet. The result we just submitted our paper. So I'm going to conclude with the nice thing that we did at NIF is we did the same thing on NIF that we did at NOVA. We are allocating 8% of the facility time, that's 18 days per year of shot time, to basic science. Anybody can propose. It's an international call for proposals. So the first wave of proposals, when we first opened up, it's called NIF Discovery Science. We had to have a name, so we called it, I tried to call it NIF Fundamental Science, and our programmatic people doing Rayleigh-Taylor, doing Rickmeyer-Meshkov, and heat transport, they were not happy with my implication that their work was not fundamental, but ours was. So we had a big debate with the external committee. I kept quiet because I was quite irritated. But the committee, Chris McKee from Berkeley, said, here's what we'll do. We'll call it Discovery Science. No one's going to object. So Discovery Science means you can go play. You don't have to ignite a capsule. You can just go take a look around and see what happens. So we're Discovery Science at NIF. This is, can you still hear me? I lost something. Okay, so this is high pressure properties, equations of state of carbon and iron as it relates to planetary interiors and hydrogen. And high pressure here in these experiments where the density is high, meaning it's a ramp compression, high pressure here means maybe 10 to 20 megabars, or say 5 to 20 megabars, that's the high pressures. Another experiment says we want to go all the way up to a gigabar. Doing that in a ramp compression is hard, but they can do that with a single shock. So this is shock hugonial in a solid spherical target of either plastic or beryllium or carbon. They're looking at different materials, but the shock itself, a single strong shock is a gigabar or lower. You can have anything you want up to a gigabar. So very strong shock physics, Rayleigh-Taylor instability, very nonlinear radiative dynamics as it affects things like the Eagle Nebula and stars that are in the star-forming region. So that I would call that star formation radiative dynamics or radiative hydrodynamics. The supernova problem goes on, the Rayleigh-Taylor instability in the presence of a very strong shock, and I showed you the radiative effects that can be occurring. So that's the first result that came out of this experiment. And then one of the more fun ones that was new to me was collisionless shock. So you collide two very high velocity, low density plasmas. One, you collide them into each other. Lots of the plasmas, there's a lot of flow coming on both sides. You collide them, but the Coulomb ion-ion collision mean free path length is very long because the velocities of the plasma are high and the densities are low. So in the absence of something else, since the ion-ion collision mean free path length is larger than the whole system size, both in space and in our experiment, no shock would form. They just interpenetrate like wind going through a screen door. But in fact, in supernova remnants, the shocks are there. So something is causing hydrodynamic behavior when in fact there should be no hydrodynamic behavior. And that something is plasma instabilities, and in this case it's thought to be the Weibull instability, makes the material behave as if it's hydrodynamic when in fact the velocities are high, the density is low. It should be just like wind going through a screen door. There should be no interaction at all. So that's neat. It forms these very sharp shock fronts. That's called a collisionless shock. The Weibull instability is thought to be the plasma instability that kicks up and gets going, that creates little magnetic fields that then cause forces so you don't get the clean interpenetration. Now, if you're an ICF person, as soon as you see a result that does not make sense and cannot happen but happened, the first thing you say, oh, it's a bloody plasma instability. Because there's many of them, right? And we suffer with them, stimulated Raman scattering, stimulated beryllium scattering, filamentation, you name it, there's a plasma instability that will get in your way and do something that's not supposed to happen. So you look at that and you say, well, heck, if it's not supposed to happen, but there it is, it's got to be a plasma instability, a collective effect. And in this case, it's the Weibull instability, and it's neat. It's what forms the supernova remnant shocks. So that's sort of the basics. Oh, and also, and it's the basis for at least some fraction of the particle acceleration that leads to the cosmic rays. And so as these teams evolve, like the team that's doing the, let's see, I'm going to skip by, I want to show one of the teams, right? So here's the team doing the collisionless shock work. Each of the teams on NIF more or less is like this, 5 or 10 people, designers, experimentalists, diagnostic people, target people, happy people, serious people. In any case, this day worked well. We're smiling. We got off 3 shots on this campaign. This was the collisionless shock campaign. And there's NIF in the background. And so the press likes this, so they like to write about this. So we get a lot of input from press in various countries wanting to write articles and want us to say something about discovery science. Papers are being written. Let's see, this is a science result I just showed you. We hold a conference every other year, and oh, by the way, so I'm going to conclude on this. I'll go to this in the next view graph. We hold a science conference, high energy density laboratory astrophysics, every 2 years. If you're interested, you're very welcome to come. It'll be next year, and it's going to be held next year in Japan. Now, they told me the city, I'll think of it. Does anybody here on the mailing list? The city has been chosen. It'll come to me, I hope. In any case, we'll be going to Japan for this. We were in France once for a recent HEDLA. So here you can see all the different laboratories around the world working on this style of laboratory astrophysics, HED Lab Astro. Here's what I want to say to John and Dick and everybody else that came to the first couple of HEDLA conferences. Everybody, and Gail will remember this. She'll be able to tell you I'm not making this up. Everybody in the conference, so after the first one and the second, we had, we sit there and we the experimenters asked the astrophysicists, what do you people want us to do? Tell us the problems you'd like us to try and develop experiments to do scaled experiments on. And everybody, I was so proud of our Rayleigh-Taylor experiment with Gail. Everybody said, we understand hydro enough. What we want is electric fields and magnetic fields put into this. Just the hydro all by itself is cute, but we could have told you the answer you're going to get. We would not have been off by orders of magnitude, which is true. In ICF, we're worried about 10% or 20%. Well, in Astro, they're worried about bigger things. So they said, we want magnetic fields into your flows or electric fields or both, and radiation. So we want good test experiments that we can test our codes against of rad hydro, not just hydro, but radiation hydrodynamics, where the radiation matters, MHD, and radiative MHD. And so, of course, I was a little, they said great stuff, but we don't care. We think we do that well enough. Do something else. It's been since 20 years, but I'm happy to say we are doing the radiative now, as I showed you a recent result, and the world is doing pre-existing magnetic fields in the experiments now. So we're getting MHD. At Omega, you can create a pre-existing field for your experiment, and on NIF, I skipped the result, but we're developing that capability also. So you'll have MHD, radiation. Well, we can do the radiative now. Electric fields probably not, but we are putting in the magnetic field, and the astrophysics community really wanted the magnetic field. When they wanted to be able to put the field in and then study something, jets, instabilities, Weibull instability, whatever. So that's happening. It took us 20 years, but we're getting there, and so hopefully we'll be here for the next 20 years doing that kind of work. So with that, John, we delivered. Dick, we got magnetic fields, so you're here. We should actually talk about the deadline. The deadline for the next proposal is September 1st. You got lots of time. We can sit down and start talking. Thank you. I'm on time, right?
Yeah, perfect.
Oof, yeah.
I tried looking up the conference, but I couldn't.
I'll show you where it is.
Yeah, if anyone knows that city, you shout it out. But I can't find it online.
Shirahama? Where was Aiched? Was Aiched in Shirahama? Then it's in a different city. I'll think it. It'll come to me. They just told me by email. It hasn't been announced yet.
Oh,